All right, so so far we've had these lengthy discussions about acidity and basicity, and we've always been talking about aqueous acids and aqueous bases. And although water is the most important solvent, hands down, um, you can also have acidity and basicity. These concepts and these ideas are applicable to non-aqueous solvents. So that's what we're going to talk about in some good detail in this video. So the strengths, the first thing to realize, which at first might be counterintuitive, but I think you'll come to appreciate it on the next few slides, is that the strength of acids and bases actually depends very strongly on what sort of solvent you're in. Okay, and so for example, hydroiodic acid, on our table, that was the one of the or the actually on our table the strongest acid listed. It had a pKa of -11. HBr, hydrobromic acid, it's also very strong, not quite as strong. But so these are strong acids in water, hands down, no questions asked. But if you put them in anhydrous acetic acid, they actually behave as weak acids. So why is that? We'll explore that in this video. Acetic acid, definitely a weak acid in water. pKa is 4.76. That's a strong acid, acetic acid is, when it's dissolved in liquid ammonia. That's interesting. Acetate, the conjugate base of acetic acid, that's a weak base in water, but that's a strong base in anhydrous formic acid. So clearly, what solvent you use really, really makes a difference in terms of what the strength of the acid or the base is. So in order to dive deeper in these concepts, we have to introduce something called solvent leveling. And so let's just go back to some basics here. So we have, a generic acid, HX, reacting with water to make hydronium and X minus. We write the equilibrium expression for this, the Ka, and we know the pK is the negative log of the Ka. And we've been saying that, if the pKa is pretty small, less than 0, let's say, that's a strong acid. And this is true. The reaction is essentially going to completion. If you have a pK of less than 0, Ka of 1 or less, 1 or greater, sorry, essentially you can rewrite this and get rid of the equilibrium expression and just have a straight arrow here. For every 1 mole of HX that reacts with water, you're going to generate 1 mole of hydronium and 1 mole of halide. And the ramifications of this are actually quite large, okay? That means that you cannot have any acid stronger. What that means is no acid stronger than H3O plus hydronium can remain protonated. Okay. Basically, if you have a stronger acid than H3O plus, you're gonna do this reaction. Okay. So hydroiodic acid is a great example. Very, very strong acid. It's a stronger acid than H3O plus. None of it's going to be protonated. It's all going to go to iodide in water. Okay. So what that ends up meaning is because you can only, for every 1 more of HI you have, you can only make 1 mole of hydronium. If you're HI or HBr, even though those have different acidities, technically, HI is stronger than HBr. They're both so strong that this reaction is going to completion. And so for the strong acids, it's actually impossible in water to discriminate between HCl, HBr, and sulfuric acid. They're all just very strong, as strong as they can be. Equilibrium area goes away, and you make 1 mole of hydronium for every 1 mole of acid present. And so how can we say then that HI is stronger than HBr? And how can we give them pKa values if we can't discriminate them in water? That's where people do experiments in other solvents in order to generate that that table that I showed you. Okay, so this idea that it's impossible in water to discriminate between different strong acids because no acid stronger than hydronium can remain protonated. This idea is called the leveling effect. We say that water has a leveling effect on strong acids, and in essence, it brings them down to the same acidity as hydronium. So even though HI is technically a stronger acid than hydronium, because you only get 1 mole of hydronium formed for every 1 mole of HI, the reaction goes to completion. HI effectively in water has the same strength as hydronium. All right, so what about bases? Similar logic here. We can set up a base equilibrium expression, a KB, a PKB, and we say that if a PKB is less than 0, we consider that a strong base. The reaction is going to completion. Now, if a PKB is less than 0, we know from our relationship pKa plus pKb equals pKw equals 14 at 25 degrees Celsius, that a pKa less than 0 is the same thing as saying the pKa of the conjugate acid is greater than 14. And so essentially in these cases, with the pKa of the conjugate acid being greater than 14, the base is completely reacting with water to give one equivalent of hydroxide. For every 1 mole of base added to water, 1 mole of hydroxide is being produced. Same exact logic here, now just on the base side. No base stronger than hydroxide can remain deprotonated. And so it's impossible in water to discriminate between very strong bases. So sodium amide, the sodium methide, these sort of very, very strong bases that have pKa's of 40 or higher, as long as it's higher than 14, they all behave the same in water. They're generating 1 molar equivalent of hydroxide. So we say that water has a leveling effect on strong bases, which brings them down to the same basicity as hydroxide. And so we can now kind of generalize this to any solvent. So now instead of saying water here, I'm just going to write this with H-sol. So it should be some generic solvent. So B base plus H-sol is going to give a deprotonated solvent anion with Hb plus. You can write, sorry, this is say pKb equals negative log Kb, but you get the idea. And if pKb is less than 0, then you have a strong base. So that reaction is going to completion. Another way of saying that is the pK of the conjugate acid must be greater than pK-sol. So before it was pKw for water, which is 14. Now we generalized it. And so this is analogous for any other solvent, where you're just going to have this 1 equivalent of base reacting with solvent to make 1 equivalent of the anion if the pK of the conjugate acid is greater than pK-sol. So what does this mean? In water, what we basically figured out is acidity can only be measured from pKa 0 to 14, okay? And why 0 to 14? That's the pKa of hydronium, okay, which is 0, pKa of hydronium 0, and the pKa of the conjugate acid, conjugate base of hydronium, water, which is 14. pKa of water is 14. So recall this auto protolysis business where you have 2 molecules of water interconverting between hydronium and hydroxide. And we said pKa plus pKb plus pKw equals 14. That is telling us this auto protolysis constant of pKw equals 14 is telling us that the acidity discrimination window width, okay, is 14. It is equal to pKw. The width from which we can measure acids is 14 pKa units wide. This goes from 0 to 14, okay? There's a little bit of a side because this is an annoying thing that happens in other courses sometimes that's actually wrong. And it's a fault of history of science that this got all screwed up. And so I just want to clarify it. If you're interested in how this is screwed up, I can send you some literature that really clarified it for me. But I was very confused by this when I was in college because I had some courses, like my inorganic courses, telling me the pK of water was 14. And I had other courses telling me the pK of water was 15.7. Okay, so this is wrong. It's not 15.7. Some courses will tell you that. You can tell your professors that I told them that this is wrong. Okay, and I'm happy to talk to them and explain to them how they should stop teaching that because it's actually wrong. And for other people on YouTube, feel free to reach out and I can maybe make a video explaining why this is wrong someday. But it takes a little bit of math and going into some details. But the pK of water is at 25 degrees C, at least 14. The pK of hydronium at 25 degrees C is 0. So if you see something else in organic biochemistry textbooks, organic or biochemistry textbooks. Don't believe it. It's wrong. Okay, it's fake news. It's 14 and 0. And yeah, actually, if you Google this, what is the pK of water chemistry Libre text? This is the best explanation I've found of why the pK of water is 14 and 0 and not 15.7 and minus 1.7. And from our standpoint, how we set it up, it all makes sense, right? It's based upon the autoprotolysis constant of water, and nothing really more complicated than that. All right, so now when we talk about solvent leveling, and now we can go back to our general discussion of different solvents. In any solvent, the acidity can only be measured, or now extending to other solvents. We had this idea that for water, we could only measure from the pKa of hydronium to the pKa of water. And for any general solvent, we can extend that to say the acidity can only be measured from the pKa of H2Sol plus to the pKa of H-sol. And that's based upon some autoprotolysis of H-sol, okay? And so, you know, you can have 2 molecules of H-sol, just like we have 2 molecules of water, going to H2Sol plus, the acid form, and Sol minus, the conjugate base. We can write pKa plus pKb equals pK-sol. And so the acidity discrimination window width is pK-sol. And so you can look at, for example, the different acidity discrimination windows of different solvents and their effective pH in water. So like take, for example, ammonia. Ammonia, the pK-sol for ammonia, pK ammonia, autoprotolysis of ammonia is 30. And so as a result, you have a much wider window in which you can measure acidity, okay? And why does it start here at around 9? That's because the pKa of ammonium, H2Sol plus, right, is 9.25. So you're ranging from 9.25 to like 39.25, roughly. All right. So what this means is that ammonia, liquid ammonia, we're talking about liquid ammonia here as a solvent. There's no water in this. Okay, totally non-aqueous. Liquid ammonia can, by the way, you have to do this at low temperature because ammonia is a gas at room temperature. It's slightly low temperature. Liquid ammonia can tolerate very strong bases, okay? And so what does that mean? That means you can have something like with a pK of 30, right, base with the conjugate acid having a pK of 30, that can be totally happy in ammonia. You can measure it. Whereas if you put that in water, you're outside the window, so you're just gonna make hydroxide when you do that, okay? Look at methanoic acid, more commonly called formic acid. This chart called it methanoic acid. The pK-sol for that is 8, so it has a narrower window than water's, which is 14. But because the pK of protonated formic acid is so acidic, it's minus 10, you can tolerate very strong acids. Strong acids will appear actually weaker in this, okay? Just like strong bases in ammonia will appear weaker than when in water. So, you know, that's just a very brief kind of introduction, a little bit of a teaser of the complex chemistry, acid-base chemistry that can occur in non-aqueous solvents. I think it's a fascinating area. A lot of people don't think about the acidity in non-aqueous solvents, but it's totally valid. And you can run reactions, you know, in totally different conditions that can give you different results. If you need a base to be really strong, you better use a solvent or no solvent at all that can tolerate, you know, that strong of a base.